0. All right, so what is the comparison test? Well, first let's summarize what we know. All right, ready? This is what we know. We have like a little grab bag or a little toolbox of convergent and divergent series of all positive constant terms, infinitely many terms, right? So let's summarize what we know. So if we can compare these to unknown series, we can figure out if they converge or diverge too. So what series do we know? What series do we know to converge? Well, there's geometric convergence series. Now remember, it's usually enough just to know that it's convergent or not. A geometric is special in that we know what they converge to. Let's say this starts at n equals 0 and goes to infinity. If n equals 0 is where it starts, the first term is 1, so a is 1. The common ratio is we're multiplying by 1/2, we're multiplying by 1/2, right? So isn't it a over 1 minus r is 1 over 1 minus a half is 1 over a half is 2? So not only do I know that it converges, I know that it converges to 2. Remember, if the common ratio, in this case a half, in absolute value is less than 1, we have a convergent geometric series. But what about divergent? Aren't these divergent geometric series? By the way, that's also known as a series that fails the divergence test. The divergence test, or Cauchy's minimal criterion for convergence of infinite series of all positive constants, states that there's no way in hell that this series can converge if the terms that you're adding up don't get smaller and smaller and smaller, and eventually their limit is 0. These terms get bigger and bigger and bigger. If n is 0, you get 1, 3/2 to the 0. If n is 1, you get 3/2 to 1.5. If n is 2, you get 9/4, or 2.25. It's getting bigger and bigger and bigger. If you add up infinite many terms that just keep on getting bigger and bigger and bigger, that's got to blow up. All right, we call that the divergence test, or Cauchy's minimal criterion for convergence. By the way, if you pass the divergence test, you still have to check if it converges. That's necessary but insufficient. All right, what else do we know? Well, based on our integral tests yesterday, we figured out that p series that convert to p integrals in the integral test converge when p is greater than 1. Now that's a p series that converges. We don't know, well actually we do know what that one converges to, but we usually don't know what they converge to, and that doesn't matter, we're just worried about whether it converges or not. So note that this, for example, is a divergent p series, because p is 1/2. Special case, when p is 1, 1 over n to the 1, is a p series, but we call that the harmonic, so I'm going to keep that on a separate burner there. How about, well, the harmonic? That's divergent. What about the alternating harmonic? Now this is weird, I'm sort of cheating. This is not an infinite series of all positive constants or all positive terms, but it's alternating, right? That's okay, but that might come in handy. That would be good to know. Let me throw in one we don't know that does converge. This one. This converges to E. If you plug in 0, you get 1 over, if n starts at 0, right? You get 1 over 1 is 1, and then plug in 1, you get 1 over 1 is 1 again, so 2. Then plug in 2, you get 1 over 2 is a half, so 2.5. Then plug in 3, you get 1 over 6, right? 3 factorial is 6, and 1/6 is 0.16666, plus the 2.5 is 2.7666. Isn't it getting closer and closer and closer to E? So yeah, I know this thing converges to 2. I know this thing converges, by the way, to pi squared over 6. This is the basis of the Riemann hypothesis. I know this, by the way, converges to L and 2. We haven't proven that yet, but that's coming. And I know this converges to E. But again, it's rare that we know what they converge to. It just matters whether they converge or not. And of course, anything that fails the divergence test or fails Cauchy is fair game for a divergent. Now, this is what the comparison test says. If you have an unknown series whose terms are greater than or equal to all the terms in your series, and your series diverges, so does the unknown series. Because if all the terms of the unknown series are bigger than the terms that you have, and you know that your series blows up, the other one's going to blow up worse. Conversely, or on the corollary to that, is that if you have a convergence series, like one of these on the left, and you're comparing it to a series that you don't know, But the unknown series has terms that are less than or equal to these. Since these converge and your unknown series are smaller terms, they got to converge to something too, right? Something smaller than whatever your series converges to. So, here's the game. Here's how you play with the comparison test. Oh, please excuse
the interruption. Stephen Dulski, please report to the main office. Stephen Dulski to the main office. Thank you.
All right, so say n goes from 1 to infinity, and you got 2 to the n over n squared. Okay, so how do you use the comparison test to prove convergence or divergence of this unknown series? By the way, the first thing you really should check is Cauchy. Does it pass Cauchy? Now remember this little rule of thumb. N to the n grows faster, then n factorial grows faster, then 2 to the n, like an exponential, so f is factorial, e is exponential, or n squared, like a power function or polynomial function, or ln of n, a log, or any constant, like 3. Okay? So notice that these rational terms, isn't this top-heavy? 2 to the n is exponential, over n squared is poly. So as n gets larger and larger and larger, these terms get bigger and bigger and bigger. The numerator overpowers the denominator, it's top-heavy. So this fails, this does not pass the divergence test. So does not pass divergence test. Therefore, the sum diverges or it does not exist. Be one with your inner low hand. Okay. All right. So first, check Cauchy. If Cauchy fails, then it's divergent. Walk away. You're done. If it passes Cauchy, if it passes the divergence test, it has a chance of converging. You got to use a comparison test or an integral test, like we did yesterday. How about this one? Sigma n starts at 1, goes to infinity of 1 over n plus 1. Now, what's your intuition? First of all, does it pass Cauchy? Yeah, it's bottom heavy. Okay. Second of all, as n gets humongous, does the 1 in the n plus 1 really matter? Isn't that basically harmonic? Oh my lord, what are you doing?
Kira Hofen to the main office. Kira Hofen to the main office.
Okay, so if you're trying to show that this is divergent, you got to show that it's bigger than a divergent series that's known. Now the game here is, if I want to make the second series smaller, I'm going to make the numerator smaller or the denominator bigger, right? And what you do is you use that n-Feppel constant thing to replace stuff. Now 1 is about as small as it gets. That's a constant, right? So I can't really make that small. Can I make the denominator bigger? How about n plus n? Replace a constant with a poly. Isn't poly bigger than constant? Eventually, at least for some n, for infinitely many n. So this is a true statement. Now, is it true for all n from 1 to infinity? That you got to finagle. If it's not true for n equals 1, n equals 2, n equals 3, that's okay. If you can do it from 3 to infinity, that's fine. As long as it's true for infinitely many n, I don't really care if I drop off the first few terms. That doesn't really affect convergence or divergence. So is it true? Let's say plug in 1. On the left, you have 1 over 2. Plug in 1. On the right, you have 1 over 2. Well, it's not less than. It's not greater than. All right, how about this? Plug in 2. 1 on the left, you have 1 over 3. On the right, you have 1 over 4. Hey, that's right. Okay, so make that starting at 2. Okay, now I don't know that they get so crazy about this on the AP, but that's technically the case. So that's a true statement. Now, is this really harmonic? Well, yeah, because you can say this. Isn't that n plus n 2n? Could I write it this way? Half of a harmonic. It's not the harmonic, because the harmonic is this starting at n equals 1, right? So this is a harmonic. So it's half of a harmonic, but harmonics blow up, so half of that also blows up. So therefore, you have to have some kind of a conclusion here. They like the verbiage. Therefore, this given series diverges by comparison to a harmonic. So you see the game here? You have to decide if you want a greater than or less than. Greater than for divergence. On the left side, we have the unknown series. So greater than to show that the unknown series is divergent, and less than to show that the unknown series on the left is convergent. And what you do is you use that n-Feppel constant thing to replace stuff on the right-hand side to make the right-hand side match that inequality, and come up with a series that you know from our little toolbox here, right? So you're going to use this toolbox And you can use that n and Feppel constant stuff. Okay? All right, try this again. What do you think of this? N starts at 0 and goes to infinity of n over 3 to the n. All right, so, by the way, this is a Pascal sheet with a divergence test. Let's see, Pauli over exponential. N Feppel constant. E is bigger. It's bottom heavy, so that's okay. So if it's bottom heavy, I don't know. What's your intuition here? Could we show convergence? Let's try it. If I want to show convergence, the unknown series on the left is less than the known series on the right. The right side is bigger. So I got to make the numerator bigger or the denominator smaller. What if I make the numerator bigger? Pauli, make it exponential. That's nice. Now, does it start at 0? Be careful with this. But notice, the right-hand side is what? Isn't it geometric? Isn't it? That's geometric, where R is 2/3 and A is, if we start with n equals 0, A is 1. So 1 over 1 minus 2/3 is 1 over 1/3 is 3. Okay. But does it work from 0 on? Let's see. The left side, if you plug in 0, you get 0. The right-hand side, if you plug in 0, you got 1. Okay. I'm going to say that's probably correct. If you plug in 1 on the left side, you get 1/3. You plug in 1 on the right side, you get 2/3. Yeah, I think that's fine. Leave it. Sometimes, though, you got to finagle where you start the n. As long as you have infinitely many n's involved, you're good. So look, this is how you use the comparison test to prove convergence. So therefore, the given series is convergent by comparison to a geometric series, and say why, where R is 2/3. As long as R in absolute value is less than 1, you're in business for a geometric series. Let's see here. Is that the only way you could have done it? Let's redo this one. Try this. N starts at, let's say N starts at 1. Let's see if we can prove it's the same series, it's just starting at 1. Let's see. What if I make the denominator, I want the right side bigger, so let's make the denominator smaller. Let's replace exponential with Pauli. How about this? Okay, now I can't, this is why I didn't start at 0, by the way. You can't start at 0, right? So if it started with 0, right? You're going to say, okay, I can't start at 0, right? Because on the right-hand side, if we plug in 0, it's undefined. Does it work starting at 1? All right, on the left-hand side, you get 1/3. On the right-hand side, you get a 1. Okay, plug in 2. On the left-hand side, you get 2/9. On the right-hand side, you get 2/8. Yeah, sounds good. But why is this good? What series is this? Well, n over n cubed, isn't that, whoops, isn't that 1 over n squared? So that's a p series. If p is greater than 2, and so it converges. So there you go. Therefore, convergent by comparison test to a p series. And what's good about this p series is that it converges because p is 2 greater than 1, in other words. Because remember, if you use the integral test on this, it converts to a p integral that converges. An improper integral or p integral that is a p integral that converges. Okay, good. Okay. Let's see. What's a good one here? All right, I think you get the idea. That's just a short overview of what we did today. There's a couple more examples. Oh, okay, one more example. There's a couple more examples on the smart notes that will be attached to the video, so you can look at that if you want. But one more like this. This is a free response question, 1975, BC5. It gives you an alternating series. N starts at 1, it goes to infinity. And it goes -1 to the n plus 1 times n cubed over 3 to the n. Okay? Now, the question, with two parts. Part A, does it converge conditionally? In other words, does it pass the alternating series test? So let's talk about that. Here are the three antecedents of the alternating series test. It's sort of like the Cuban theory, theorem. Okay, I. Is it strictly alternating? As you plug in 1, n is 1, n is 2, n is 3. Do the signs change every single time? Positive, negative, yes. Or forget the signs for a second. Look at the absolute value. Are the terms decreasing? Well, look, n in Feppel constant. Isn't there a exponential on the bottom and a poly on the top? That's bottom heavy. And I think if you convert that to a continuous function in x and find the derivative, it's going to be negative. You could do that. And is the limit 0? Does it go to 0? Yes, I think it does. So those are the three antecedents of the alternating series test. And if you meet all three, then the series will converge. There you go. Another thing that's nice about the alternating series test is if you want to estimate its value, you can't actually add up in infinitely many terms, right? You can do a convergence test and you got to stop somewhere. I mean, a convergence table, and you stop somewhere. But what the alternating series test corollary says is that wherever you stop, let's say you add up like, I don't know, 100 terms. The first term you leave out, the absolute value of the error is less than the absolute value of that term. Why? Because you're not really adding and adding and adding infinitely many positive constants. You're adding, you're subtracting, you're adding, subtracting, and you're adding a certain amount, then you're subtracting a little less. Then you're adding a little less than that, and you're subtracting a little less than that. So you're sort of approaching a limit, sort of like with a sandwich theorem. So if you stop with you've added a positive amount, your overestimate is no more than the absolute value of the next negative value, a term that you leave out. And likewise, if you add a negative part, you're within the right answer to within at most the next term you leave out. Okay, so that's going to be nice when we talk about error analysis. We'll get to that. All right, so that was part A. Does it converge? Yes. That's called converging conditionally. But part B says, does it converge absolutely? And that means take the absolute value. That. And what do you think? Does it converge absolutely? Let's move this over here. If you make all the terms positive, now that's going to be hard. It's harder to converge absolutely because you're just adding and adding and adding, positive number, positive number, positive number. That's hard for it to converge, right? It's easier to converge if it's alternating. Well, can you do a convergence test? Now we already know that the terms are decreasing, right? So it's bottom heavy, so it passes Cauchy. That's not the issue. Do you think it converges? Well, if you think it converges, let's make it less than something we know. And so we're going to have to make the numerator bigger or the denominator smaller. Can we make the numerator exponential? How's that? That's a true statement. Well, is it a true statement for all n? N equal 1 on? Let's see. If I plug in 1 on the left, I got a third. Plug in 1 on the right, I got 2/3. Yeah. If I plug in 2 on the left, what do I got? I got 8 ninths. 8 ninths. If I plug in 2 on the right, I've got 4 ninths. Wait a minute. That's weird. It's true for 1, 1/3, and 2/3. It's true for 2, 8 ninths, and 4 ninths? No, it's not. Is it true for 3? 27 27ths, right? On the left, on the right, 8 27ths. Wait, something's screwy here. All right, this one's going to be hard to figure out where the end starts. I don't have a lot of time right now. I'm gonna stop here. But what I would do is graph these and see when 2 to the n over 3 to the n is greater than n cubed over 3 to the n. And from that point on, I don't know, n equals 5 or something, you should be able to say this. I'm not going to spend time on that right now. I'm just going to say that, yeah, this is less than is a true statement. The n equals 1 is not quite right. But this is geometric, isn't it? And it's convergent geometric. So I'm going to say, yes, it converges, the original series converges absolutely by comparison to a geometric series where r is 2/3. In other words, it's less than 1 in absolute value. Okay, let's leave it at that. That's going to be the last recording in Unit 10, series of constants, infinite series of constants, convergence or divergence, Chapter 10, Section 5. All right, so that's it. Have fun, YouTube. I hope that was helpful. Bye-bye.